Hello and welcome to this short video where we're going to talk about the solution to this one example problem. Here we're looking at a problem that involves friction forces. It involves how friction forces can affect one object from another according to Newton's third law, and we're going to discuss non-inertial reference frames. So to summarize, we're going to have friction forces. We're going to have Newton's third law, front and center, and we're going to have non-inertial reference frames. Now, non-inertial reference frames are associated with what are called fictional forces. These are forces that don't exist if they're measured in an inertial reference frame. In other words, they're a misuse or an incorrect use of Newton's second law, but if you are aware of their limitations and their relative acceleration to an inertial reference frame, then you absolutely can solve problems with them. And what defines a non-inertial reference frame? It simply is any reference frame, which is a place where you make measurements, where the acceleration is non-zero. So it's just any reference frame where the acceleration is not equal to zero. It could be a constant, it could be a non-constant, but the important thing is it's just not zero. So let's take a look at this problem and get started. So we are given the mass of two separate blocks, M1 and M2. We are also given the friction coefficients between the blocks, which is mu K1, and we're given the friction coefficient between the bottom block, M2, and the table, which is mu K, okay? Which could also be labeled mu K2, but we'll stick with this subscript because at least they have two separate names. And we also have a single external force other than gravity, which is the tension force, which is shown here acting horizontally. So let's take a minute and fill in all of our forces in this diagram. In other words, let's draw a force diagram. All right, so let's do this one block at a time. If we look at just block one, we know that indeed we do have a friction force already drawn. We're also going to have a gravitational force, which is going to be M1G. And we're going to have a friction force, which is going to act backwards, like so, and that's going to be F1. All right, now we also have a normal force, which is going to be the equal and opposite in magnitude to M1G. In other words, M1 pushes on M2, M2 can't move because it's on a rigid table, and so there's a exact opposite normal force. Essentially, it's because there is no acceleration in the y direction. And as far as directions are concerned, we have the x direction and the y direction. Okay, so those are all four forces acting on block one with mass M1, the top block. But what are the forces acting on the bottom block? Well, there's no external tension force, but there's still gravity. So we'd have some M2G. And there are definitely some effects from the friction force. Well, from friction forces. Because if you look, we're told that there is a friction coefficient between the block and the table, right? As I pointed out, with a different friction coefficient, lower, by the way, than the friction between the blocks. And that means that there is going to be some friction force pushing back, preventing the block from moving. Now, I'll talk a bit about our expected direction of movement here, which is a pretty safe bet. So we'll call that F2. Yeah, and you know what? I'll add a 2 up here as well in the body of the problem. So you know that the friction coefficient 2 corresponds to block 2 in the table and corresponds to friction force 2, right? In terms of clear labeling. All right, now here's where things get interesting because there are going to be two more forces. One of them certainly is going to be a normal force, but it might not be the normal force you expect. And we'll speak to exactly what it's going to equal, and we'll draw it like this. So there, for now, we'll just call it the normal force. And then let's think about what is the, kind of the last force acting on this block. Well, kind of two more. But first, one of them is that direct consequence of Newton's third law, because there's a friction force that's slowing down block one right? Because block 1 wants to go in this direction. It has a movement, a velocity in this direction. And if it doesn't, then that simply means that there's no movement at all. That would be the case where the external tension force simply isn't big enough to overcome the friction force. It is in this case. In that case, we shouldn't be using the kinetic friction coefficient. We should be using the static friction coefficient. But there's going to be movement here, so great. Now, if there is movement, that means there has to be a reaction to the action force. Okay? Well, what am I talking about? Well, in this case, the action force is actually going to be this original friction force because it's happening from some external effect, at least from the perspective of block 2 at the bottom, right? So there's this external effect of friction acting on it, right? Because, if block 2 is a table, then we just say, oh, the table can't move. But of course, block 2 is capable of moving. And so therefore, we need to consider its acceleration. So we must consider the reaction force to friction force 1. Okay? And reaction forces by Newton's third law are always equal in magnitude, but opposite in direction. So that means there's going to be effectively an external force acting on block 2 of FF1 that wants to pull block 2 towards, well, the right, in the same direction that block 2 wants to move. Okay? So essentially, block 1, as it's dragged across block 2, wants to pull block 2 with it, which is a very real life situation. Okay? So those are the forces acting on block 2, but I hinted at something else we should, consider, and that's because if you consider this gravitational force, right, the one that was just some external force, right? The Earth was pulling on block 1. Well, here's the thing, right? If block 1 was just sitting on a rigid table and the table wasn't going to move, then simply we wouldn't care anymore about this force. We'd be done with it. Now we might need to consider it for the purpose of calculating the normal force, because the normal force will allow us to calculate the friction force based on the friction coefficient, which is a normal process of solving problems that involve friction. However, in this case, since we have another free body, the block underneath block 1, well, that means that gravitational force needs to be further considered. It's actually pushing on block 2, right? Of course it is. And what that means is that it's an external force acting on block 2. So then that means that the total sum of vertical forces acting on block 2 are going to be, at least the downward ones, are going to be M1G and M2G. So what does the normal force have to equal if there's no acceleration in the y direction? The sum of the two. In other words, the normal force isn't just equal to M2G, it's equal to the sum of M1G and M2G, because this is effectively another force acting on block 2. Okay? Now, I'll just leave it where it is because it kind of already looks like it's acting on block 2. But if we weren't even going to draw block 1, if we wanted to maybe draw 2 completely separate force diagrams, then we might draw showing coming directly out of the bottom M1 to show those are clearly 2 downward forces pushing block 1 into the ground or the table. Thus, the table has that reaction force of the normal force. Okay? All right, so with all that explanation, we better get to actually writing our equations. Okay, so we're going to have 4 equations of the forces in the x and y direction, because we'll have all the forces on 1 in the x direction, block 1, all the forces on block 1 in the y direction, all the forces on block 2 in x and y. Okay, so a total of 4. So we have F net 1x, F net, right? Net just means sum here, 1y. I'm going to put a little colon here. You can put an equal sign, but ultimately I want to actually write out what all those forces are and then have them equal, M1, AX, and so on. So we'll just think of this as sort of a summary. Then we will have F net 2x and then F net 2y. All right, so what are all the forces at play here? Well, we've talked about all of them, so we should just be able to write them down. At this point, I'm just going to write them down with the similar labels as in the force diagram, and we'll expand them with all of our known values in just a minute. Okay, so in the x direction on block 1, we have the external tension force, right, going in a positive direction. So just Ft, And what about in the negative direction? Well, just minus F, F1, okay? And that's going to equal M1A, okay? Now, here's an interesting thing. Is there just one acceleration here? No, okay? So I'm going to call this A1, but we're going to relate A1 and A2 in just a minute, okay? So that's it for the x direction of the forces acting on block 1. What about in the y direction? Okay, so in the y direction, we are going to have the normal force pointing up based on our choice of positive y being up. And we're just going to have, we could have called this the, gravitational force over here, right? We call this FG1, but I went ahead and already split that into M1G, which is kind of, a natural step. Okay, I don't do that with all the forces because some of them are more tedious to talk about exactly what they're expressed as, and it's better suited to further steps in our solution. But the idea that gravitational force is always mg is a great kind of idea, something you can work with from the beginning. Now, are we going to have acceleration in the y direction on block 1? No. Okay. There simply is. There's absolutely no reason to expect it because these two forces, they are the gravity isn't going to be able to pull the block down because we have a rigid surface underneath it. So we have an equilibrium case. And we even if we had, say, a component of the tension force, right? Say acting up like this. If the tension force was in this direction instead, we'd still probably, would have to check and see if the vertical component of the tension force was actually large enough to lift the block up, and most likely it wouldn't be. So point being, we have 0 here, not because there's 0 mass, right? It's still M1A, right? The problem here is that there's just simply no acceleration. Not a problem, but the reality. Okay, so now on to block 2, a bit more going on. So with block 2, what force do we have in the positive x direction? Well, in fact, we have the friction force. Now, this is so counterintuitive on the one hand because, one of the ways we think about the friction force is it only acts, to oppose motion. But this is actually driving motion. Well, that's because, this is the reaction to the friction force. This isn't the original friction force. This is what the friction force can do as a cascade of effects, okay? Which just has the same name, right? Because, of course, they have to be equal in magnitude. Now, what else is going on in the x direction on block 2? Well, the other thing that's going on in that direction is an actual, opposing force that's trying to prevent the motion of M2, and that's going to be F2. Okay. Now, if there was no friction between the bottom block, the larger block, M2, with mass M2 and the table, then there simply wouldn't be a second friction force. Okay. Block 2 would get driven entirely by however large the friction force acting on the top of it is. Okay. Any other forces in the x direction acting on block 2? Nope. So that's just going to give us M2A2. Okay. So then carry on to the forces in the y direction. This is definitely the most we have, right? So we've got 2 downward forces. Right. So I had left an equal sign there, right, when I was explaining something. So, but what are 2 downward forces? We have M1G and M2G. Okay. So, and 1 upward force. And I actually should definitely differentiate between the 2 normal forces. This would be normal force 1 and normal force 2. They're definitely not equal. They need to have separate labels. And we will, define them as we move on. So our only upward force in the, so the only positive y force is Fn2, so the normal force acting on block 2. And then our 2 downward forces are going to be M1G and M2G. And these are going to equal 0 again. Again, no acceleration in any of the y directions. Okay, so if you look then, kind of good reality check, what are we actually trying to solve for? Well, precisely the accelerations. We want to know the acceleration of the top block relative to the bottom block. Okay, that's going to be A1. Okay, I'll explain why that is in a minute. Then we want to know the acceleration of the bottom block relative to the table. Okay, well, that's going to be A2. Aha. And then we want to know the acceleration of the top block relative to the table. What's that? Well, this is where we have this idea of relative motion, okay? And why, why this concept of non-inertial frames, reference frames, matters so much. Because block 1, not 2, block 1 is absolutely non-inertial. So when you think about the forces, they are non-inertial. Okay, because block one is accelerating. So the actual forces acting on it, and the existence of forces, they don't tell us what's happening, right? In other words, we might say, well, if we were just to look at block one, right? So imagine that, say, block two had another force acting on it that was pulling in the opposite direction. And so then you said, if you looked at block one, then, from the perspective of, the non-inertial frame, right? In other words, the block two was so large you couldn't see the ends of it. Then you might say, oh, well, block one is at rest, right? Because maybe block two, right, the bottom one, is getting pulled backwards at the same rate that block one is getting pulled forwards. So then, if you're just looking at block one, you'd say, oh, it's at rest because the ground is sliding one way, there's a force pulling, block one the other way. It doesn't actually look like it's moving, right? So you'd say, oh, well, it must be at rest because there's some force that's keeping it at rest, right? There's a large enough force that's keeping it at rest. But there actually isn't, right? That perception of there being another force that would be keeping block one at rest is a fictional force. It's the same fictional force that's known as the centrifugal force, or the same type of force, because the centrifugal force is a fictional force that is only perceived in non-inertial reference frames, whereas the centripetal force is an actual force which is measured correctly using Newton's laws in an inertial reference frame. And Newton's laws only apply to inertial reference frames, okay? Take off the non, you got inertial frames. All three of Newton's laws only apply to them, okay? In fact, the first law really kind of establishes that whole idea, which is the law of inertia. So the second two laws are the ones you have to worry about. F equals ma, and the force pairs, equal and opposite forces, actions and reactions. Okay, then what would be another example of a fictional force, a force that doesn't really exist and only appears to? Well, a good one is what happens when you slam on the brakes in a car, right? If you slam on the brakes in the car, loose objects in the car, they appear to fly forward, right? Well, we know they fly forward because they want to stay in motion at whatever velocity the car was going at before you slammed on the brakes, right? There was an external force acting on the car. From the perspective of the inertial reference frame of, say, the side of the road, we can clearly see that it's friction that slows the car down. But naively, inside the car, you might say, oh, there's some huge force, like a magnetic force that's pulling everything towards the windshield. Okay, you wouldn't really, but that's the idea of a fictional force. There would appear to be, naively, a force that's pulling everything to the front of the car. But there isn't really, right? In fact, what there really is just inertia. Objects want to stay in motion unless there's some force, that is, to prevent them from staying in motion at that particular velocity. Okay? So that would be another example of a fictional force. All right? Now, some are more obvious than others. A lot of people think the centrifugal force is real. In fact, it's not, right? Only a centripetal is. Okay? So, it kind of depends on, what the system is and how good our intuition is. So, point being, we have great example of a non-inertial reference frame for block one, okay? So if we just look at, the forces that are acting on it and, its apparent motion relative to the table, right? We could get the wrong idea unless we, realize what's happening. Okay, and what is happening? Well, right, the actual acceleration of block one relative to the table can be thought of in terms of a vector sum, okay? So we could say that the acceleration of one relative to the table, right? So we say relative, rel for short, one table is going to equal the acceleration of one relative to two plus the acceleration of two relative to the table. Okay? So, that's the thing. This acceleration, the acceleration of one relative to two, that is not an actual acceleration, okay? Because it's measured in a non-inertial reference frame. So, it's going to be accounted by fictional forces, right? Because whatever that acceleration isn't actually happening. Because, for example, it could be at rest, right? Because if block two was moving backwards at the same rate that block one was moving forwards, right? The same acceleration rate, because there's no constant velocity here. Okay? But that, if that was the case, as I said, there'd have to be some explanation for it. And the only explanation would be a fictional force. Okay? So on the one hand, we have a great equation of relating A2 and A1. And on the other hand, we have a conceptual understanding of what's happening here. Okay, well, I think we're good to proceed with actually solving for our accelerations. All right, so the first thing we asked for is the acceleration of that top block, with mass m1 relative to the bottom block. Okay, not an actual, inertial acceleration, but still something that is, we can totally solve for, right? And could have some real life effects as long as we're aware of its limitations. All right, so let's find it. All right, so that would be solving for A1. So let's go ahead and look at the first equation that makes sense to look at, the only equation that actually has A1 in it, and think about, can we solve it directly, or do we still have some unknowns? Okay, so we definitely know the tension force. That's going to be something we know directly in newtons, so we could just plug that right in if we wanted to, but we won't, because we have to rewrite some other expressions, namely this second force here, FF1. Okay, so this one is going to be defined by definition as mu k Fn, okay? Specifically mu k1 times Fn. That's always the definition of friction force. It is the friction coefficient times the normal force. Heavier objects with the same friction coefficient have a greater friction force, okay? Heavy objects with a very small friction coefficient, so really smooth surfaces, would have a smaller friction force. So it's always the multiplication of those two variables to actually get the friction force. And then that's simply going to equal m1a1. Okay, now what is the normal force? Well, the normal force we can find directly from the sum of forces in the y direction. It's just going to equal m1g. Okay, so let's write that here, that we know from this equation here, the sum of forces on block 1 in the y direction, that the normal force, which I left off a label on it again, this would be 1, all right, and then that would be 2. Okay, at least I labeled the normal force on block 2 as Fn2, okay? Because again, they're not the same normal force. So Fn1 is going to just equal m1g, okay? So then we can go back and actually solve for that acceleration. So we have A1, okay, and then that's going to, well, here, we'll rewrite it, and then we'll solve for A1. So that's still F2, just a number, okay, and then mu k. Now I'm going to replace the normal force with what we know to be m1g, okay, and then we have m1a. Okay, so then actually solving for the acceleration, go over here, we then have that A, this would be A1, is then going to be just F2, FT. I saw the T, I said 2, but it's tension force, FT, minus mu K M1G, and then divided by M1. Okay, so that is going to be our first acceleration, and I'm going to have to make a bit more space here. So we'll resize some things, and then we'll actually plug in our first set of numbers. All right, we got our important relative velocity equation there. This was a sum of our ideas, so I'll move this out of the way somewhere. All right, maybe we can fit it up there. Key things we're going to do. All right, non-inertial, there's the definition. All right, and we'll start working on our solution right there. All right, looks good. Okay, so let's pull up a calculator here and do our first calculation. All right, so clear some things out. Okay, so let's plug in our numbers. So the first one we got is going to solve for A1, and I'll go ahead and label things as we go, especially because we're going to want that relative velocity, so we'll have to refer back to this. So A1 is then going to be our tension force, which was 36 newtons, okay? And then we have our friction coefficient, mu k1, which is going to be 0.415, okay? And then times m1, 2.97 kilograms, and then times 9.8 for gravity. So that's everything in the numerator. Then we'll go ahead and divide by m1, so just 2.97 kilograms. All right, so our acceleration is 8.05, okay? Now this, all right, is not an acceleration that we could use with Newton's laws. Okay, not 100%. It's still totally valid, but it's a relative acceleration because it's an acceleration in an accelerating reference frame. Okay. Okay, so there we have our first value. Well, let's go ahead and move on to the second one. What is the acceleration of the bottom block relative to the table? Okay, so this one is going to be inertial, which is excellent for our next step here. All right, and excellent for understanding part C. So let's go ahead and work on that. Okay, so how would we go about solving for A2? Well, kind of similarly, we're going to look just at what's going on in the x direction, because initially that's the only equation that has A2 in it, and then we're going to use our forces in the y direction on block 2 to actually solve for these friction forces, okay? And we know one of them is already, because FF1 is still just going to be, mu k1 m1g, so that's we can actually do that right away, okay? So let's go ahead and using our sum of forces in the x direction, I'll zoom out so you can see everything. We would have this first term, and just immediately rewrite it as, because we already know what it's going to become, mu k m1g, okay? We were able to do that by actually, doing a substitution, as I showed above, right? But we've already done it. It can't change, so that's the same force, okay? Then we're going to have our opposing force between the bottom block, with mass m2 and the table, which is ff2, and that one, okay, that one I'll save as a two-step process, but we'll initially put mu k2, okay, and then we'll just call that fn2, or rather multiplied by fn2. Now, if you look, you can kind of see what maybe, I look ahead, what fn2 is going to become, right, with that important, idea that there are two downward forces acting on the block. Therefore, the table has to push back, to oppose both of them. Okay, and then finally, those are just going to equal m2a2. Okay, so then that very next step is what I was referring to. We're going to solve for Fn2 using our sum of forces on block 2 in the y direction. So that just tells us that Fn2 is going to be, well, let's factor the g out, and you see just m1 plus m2. Okay, so I rearranged things, but all I did was just move both of these terms over to this side, so they both become positive, and it's just m1g plus m2g. The g factors out, and then, of course, there's your sum of masses, okay? So then we can substitute that right back in, and we'll have a nice expression for all the forces in the x direction, the accelerating direction, on the bottom block with mass m2. Okay, so mu k2, okay, which I left off the label there, but now it's added back in, g, okay, and then, oh, actually that was mu k1, excuse me, because that was the one acting from the top. There we go. I'll correct it here as well. See, you leave off a label and then you misidentify what things are. So keep all your labels. Okay. And there's mu k2, right? Because different friction coefficients. And this one will just be g, which I pulled in front, and then the sum of the masses, right? The order doesn't matter with all this multiplication. And then over here, we just have our m2a2. All right. So then we're in good shape to actually solve for a2. So let's just isolate that acceleration of block 2 relative to the table, all right, in the inertial reference frame of A2. Okay, so then we would have, can we factor anything else out? Well, certainly the G we could, all right, so I might as well. Okay, and then we'll have mu k m1, and then minus mu k times the sum of masses, mu k2 that is, and that's 1. Minus mu k2, all right, times m1 plus m2, okay, and then all divided by m2, okay? And you should always kind of expect that to happen, right? That it's going to be the inertia of whatever is moving that ends up in the denominator. And of course, in this case, the only thing that's free to move is m2, and we're just looking at the forces acting on m2. Likewise, right? What was in the denominator when we found the acceleration of block 1? Well, just m1. Okay, all right, at least the acceleration relative to block 2, that is. So let's actually find the values, the numbers here. So we'll plug it in. Okay, so for A2, then we have our subscript. Okay, so with the G out in front, Okay, 2 equals 9.8, okay? And then times, and we'll open parentheses to have our numerator, and then we're just going to have our mu k1, which is going to be the 0.4 there you go, 415, okay, times m1, all right, and m1 was that 2.97 kilograms, okay, and then minus, and now it's the first time we used it, so I'll check. So mu k2 is 0.291, right? That's the friction coefficient between the block and the table. Friction coefficients are dimensionless. They are just the ratio of the normal force and the friction force, right? The larger they are, then the more effective friction is, right? The stronger it is. And then our sum of masses, so 2.97 plus the value we haven't used, 13, the larger mass of the larger block. Okay, all right, there we go. And then we're going to divide that all by just 13. All right, so here we have our acceleration. All right, so what is this? What are we looking at here? So let's think. All right, so we have the friction force is, this is interesting. So we have such a large mass on the bottom that we actually have no acceleration of block 2, okay? So in other words, block 2 is so massive and its friction coefficient is, relatively large that it actually isn't capable of moving. So that means that we probably should make some changes to our values because I want it to move, okay? So on the one hand, we can make it lighter. That would be a pretty reasonable fix. The other is we could just make there be less friction between that bottom block, block 2, and the table. So let's see if we say make it have a mass of, instead of 13, we certainly want it to be bigger. Just kind of make it have some logical sense here. But what if we say make it 5 kilograms? All right. Let's see if that would allow it to accelerate, because it wasn't my intention to have it not accelerate for a number of reasons. First of all, it means that our relative acceleration that's asked in part C isn't that interesting, and it also means that giving a coefficient of kinetic friction right here isn't relevant, right? If anything, we need to know the static coefficient of friction, which we shouldn't assume is the same number, so it'd be kind of essentially missing information. So instead, let's change the value to 5 and see if we have a positive acceleration. Because I do want to make it clear that when you do get a value like this, you have a negative acceleration. Well, since this negative acceleration on block 2 could only be created by friction, literally pulling block 2 back in the negative direction, so essentially pulling it back in this direction, well, that can't happen. Friction can't create acceleration. It can oppose acceleration. The reaction to friction can create acceleration, but friction on its own can't. So if we have a negative acceleration for block 2, that just means that it's at rest, and that negative number is incorrect. Okay, so it'd be sort of it'd be a case where you say, oh well, this it just means it's at rest, and this number doesn't have any physical sense. In the same way that if you solve an equation, you have a negative value of time, it just means that that event never happened, right? Or maybe that particular solution isn't the one to accept. Okay, but regardless, with our adjusted numbers, let's see if things will work with 5. All right, so if I change this over to 5, all right, still negative. All right, so what if we make the friction coefficient smaller as well? Let's make this 191. Now, might do the trick because we're getting close at this point. All right, so a little bit less friction between the table and the block. Okay, so we'll change that up. And this doesn't affect anything else in the system. All right, okay, still have a negative because there's only so much force that's actually pulling it. Because the only external force that's pulling it in the positive direction is just, it's just that friction force. What if we make it 091? There we go. All right. All right, so it's it's smooth, but still, relatively realistic. We could certainly have, those are friction coefficients that exist between, things like Teflon and so on. All right, cool. All right, so we fixed our system here, at least, for the for the sake of, kind of illustrating an idea by making block 2 a little bit lighter, a little bit less massive, and having a little bit less friction between that block and the table. Okay. Okay, so there's our new values: 5 kilograms for block 2 and a friction coefficient between block 2 and the table of 0.91. All right, so let's make sure we have everything. Obviously, I haven't corrected it completely because we still have the larger mass in the denominator, but that won't make a negative, so that's fine. And there we go, okay? So there is our acceleration of block 2, a positive value, which means it is in fact moving, okay? It's being pulled by the friction that exists between the block that's sitting on top of it and itself, okay? And, and that's, being opposed by, the effect of the friction between it and the table, but not enough to actually keep it at rest, okay? Because we fixed the numbers, okay? So if the fixed numbers, which I'll go ahead and write in so that you see them one more time, right? I wasn't before because, they were all the values we'd seen, but with this last minute change, I'll call attention to them. So 0.415, the friction coefficient we didn't change, 2.97, the unchanged mass of the block. Another way, by the way, that we could have, sort of like made sure that block 2 got pulled along, that had a non-zero acceleration, is to either make this value of friction larger, so to just have a larger friction coefficient between the blocks, or to make block 1 more massive, up to a point, because making block one more massive has the side effect of meaning that there's overall more force pushing into the table, which makes whatever friction there exists between the table and block 2 kind of more effective at slowing it down. So it's kind of a double-edged sword in that case. But if but on the other hand, that is at least could move us in the right direction, right? In terms of having a system that accelerates. Okay, so then minus now 0.091, I believe is our corrected value. Yep. And then the sum of masses, so 2.97 plus 5, all right, I'll put the units out in front, kilograms. All right, and then divide all that by 5 kilograms. Okay, there we go. Okay, and we'll put some units on the acceleration, meters per second squared. And so that gives us our value for the acceleration of block 2 relative to the table of 0.994 meters per second squared. Okay, so we're almost done. We've got our 2 accelerations, right, by considering all the effects of forces. And now we'll finally just circle back around to that idea that I mentioned quite a bit about this, this idea of relative accelerations. What does it mean to be non-inertial? Okay, well, it really comes down to this, right? Because this acceleration of block 1, right, the one we solved for, it's relevant, it's happening, right? Block 1 is moving relative to block 2, okay? It's accelerating across the top of it, but it's not like going to be explained by forces, not completely, right? Because if we looked at its acceleration, we looked at that value of 8.05, it wouldn't make sense, right? Because we'd say, oh, what's driving that acceleration? What's making it move that fast, right? Well, we know that what's actually happening, right? The actual acceleration isn't, that's not its acceleration relative to the ground. That's just its acceleration relative to something else that's accelerating. So the only way to find its acceleration relative to the ground is to take the sum of the accelerations, okay? The vector sum. So what we need then is we need that the acceleration of block 1 relative to the ground, all right, is then going to be the sum of the 2, okay? Now they're both moving in the same direction, okay? So there's no subtraction, okay? If say block 2 was accelerating in the opposite direction, then there would be subtraction to consider, okay? We'd have to realize that, that means that, that the actual acceleration of block 1 relative to the table, right, could be less than it appears, okay? Right? But in this case, it's going to be more than it appears because it's on something that's sliding in the same direction as it. Now that we've corrected values, at least, okay? But, corrected them or just changed them, right? Made them, illustrate what I wanted to. So at this point, we really can just plug in the numbers. Okay, so we know that the acceleration of block 1 relative to block 2, and I'm just referring to this equation right up here, all right, well, is just 8.05. That's this one, all right? And then the other one, acceleration of block 2 relative to the table, is exactly 0.994, okay? So we are on our last step, 8.05 meters per second squared plus 0.994 meters per second squared. So in an inertial reference frame, okay, so just a minute ago, the video cut off, and what I was speaking about is this last step about summing the accelerations, okay? So I think the last thing you saw that you were just looking at summing the accelerations of block 1 relative to block 2 and block 2 relative to the ground, okay? So you can see that was the step where I accidentally cut off the video. So picking up, we just want to, basically mention this last step because now that we have all our numbers in front of us, we can make our calculator a bit smaller there. And all I want to say is that, so we look at this and I make a big deal about, forces being real and only being able to use Newton's laws and inertial reference frames. So let's just quickly reflect on that one last time. Okay, so we look at this value here, right? 8.05. So that is not the block's, actual acceleration. Now, you could measure that acceleration, relative to block 2, and sure, okay, that's great. Relative to block 2, that's its acceleration. But it's not its acceleration for the purpose of Newton's laws, plain and simple. Okay, we can't apply Newton's laws. We couldn't say, understand the consequences of action-reaction pairs, understanding the ideas of inertia, or even F equals ma. Okay, now it's like that. Those limitations may or may not come up, right? But simply put, this is just what it is. It's a relative acceleration. Now, almost a better way of thinking about it though is consider this, right? Because this is the acceleration of block 1 relative to the ground. 9.05. This is its actual acceleration, all right? So when you look at it, that value, right, and we say, oh, okay, so that's how fast it's actually moving relative to the ground, right? Well, this is interesting because you say, okay, well, what force is necessary to create that acceleration? Well, it'd be a bigger force than the actual external force, the tension force that's acting on it. So if you didn't know that block 1 was on something that was also accelerating in the same direction, then you might think that there was a larger force at play to create this larger acceleration. See, that would be that idea of a fictional force, a force that doesn't exist, but naively, could be applied to explain this larger value. All right, but what's the correct explanation? Relative accelerations and non-inertial reference frames. Okay, all right. Well, that does wrap this up, right? And hopefully this solution kind of gives an idea of a few crucial ideas of applying Newton's laws, force diagrams in a more complicated way, definitely a next level way, but it's showing their real application and getting you to think about their many uses. I hope this video has been interesting and informative. Thank you for watching.